we are working on heat transfer, okay? So relatively simple chapter, not too difficult, but let's look at it, yeah? Okay, here we go. We have heat transfer. Okay, so first thing first, when you ever think about heat transfer, the first thing that should come to your mind will be how heat is transferred. And we know heat is transferred always from the hotter region to the cooler region, never the reverse, okay? That's important thing. Okay, so let me introduce you to our secondary science department. We have teacher Teddy, which is the HOD of the science department. So he's been around, he's been teaching for over 9 years. Okay, he has a particular bias to students who can dance and play volleyball. That means he himself can dance. Okay. We have Teacher Bell. Okay, Teacher Bell was actually teaching the Site 1 webinar. She's also a lower secondary science teacher who loves chemistry and traveling just as much. And then we have me, Teacher Manpreet. Okay, I am Teacher Manpreet. I also teach lower secondary science, over 13 years experience, and I love hot chocolate. Okay, it's the best thing created. And again, like I said, follow us. Okay, you can find us on Instagram, on TikTok, okay, to follow our events, to follow activities that the teachers are doing or what we have in stock for you, okay? You will be able to see even little math hacks that can help you, all right? So follow us, okay, on our platforms. All right, so let's get started with our heat transfer. Okay, so here we have the first question. Now, object X, you are told, has a melting point of 111 and boiling point of 116. So which of the following conditions does it have the least density? Okay, so we just highlight and annotate the important portions. Okay, here you are interested to know, okay, it has melting point, it has a boiling point. Okay, and you want to know when it has the least density. Now, when does it have a least density? The density is always the least when it is a gas, right? So here, the question is asking you at which temperature is it a gas? So we know, okay, melting point. So we can just draw it out. We call it a temperature line. So 114, we have the melting point, and we have the boiling point, which is your 184, okay, degrees Celsius. So before it melts, it has to be a solid. After it melts, it is a liquid. After it boils, it is a gas, okay? So here we want to know gas, right? We are interested in this portion. So very quickly, if you go through all of these options, it's very clear and very obvious. Our answer will be D, okay? 185 degrees Celsius, because it would have already boiled at 184. All right, this one, bimetallic strip. Now, bimetallic strip is actually quite frequently tested in your WAs and in your test. So something that you need to take note of, okay? Now, what do you understand about bimetallic strip? Now, bimetallic strips, they actually bend according to the temperature change, right? So what do we know? When temperature is high, so when you have a higher temperature, we know expansion happens, okay? Very easy, yeah? So, and then we know when there is lower temperature, the reverse happens. You have contraction taking place. So this concept is applied in your bimetallic strip. Now, students often confuse this question by not knowing where each strip is supposed to be, okay? So rule of thumb is very simple. The one that expands the most will actually bend the most, okay? So we look at this two. So here you are told two pairs that are heated, okay? So that means high temperature, increase in temperature. What you are given is expansion. So you want to know which of the following is incorrect. So take note, incorrect, not correct, incorrect. after heating or cooling them. Okay, so they're looking for different variations. It's given you these two separate variations and they want to find for other variations. Okay, so before we even go into the question, let's first analyze what is given here. Okay, so here R is below, Q is on top. Okay, what does this tell you when it's heated? Now it tells you that R expands the most. Okay, in comparison to Q. And in this case, Q is below. So it tells you that Q expands, okay, more than P. So if it expands more, will you expect it to contract more? Yes, we also expect it to contract more. Okay, in your syllabus, I'm sure you learn about the expansion and contraction in your bimetallic strip between brass and iron that you know, right? That what happens. So in this case here, we are looking for the option. So let's look at it. Now here R has expanded more than P. Now, is this correct? Will you expect this? Yes, correct. We will expect this. So this is a correct. Take note, question 1, incorrect. So we don't want the correct answer. We want something that's incorrect. Okay, so let's look at B. This is cooling. So we are talking about contraction. Okay. Now here it shows that P contracts most compared to Q. Now, is this true? Is this correct? Now, P is on the top. Q is below. Any idea? Do you know? Not sure? Doesn't matter. We can go to the next one, okay? Here, R. R is on top, Q is below, okay? R has, okay, they're saying that Q will actually contract more than R. Okay, we know this is it correct? It will contract more, yes? Not sure? Okay, never mind, we go to D. You see D, yeah? Again, you're not sure, it's totally fine, okay? MCQ is always like this. You always have some unsure components. Okay, here, P, and you have R. Here, R is below, okay? P is on top. So here, it has contracted compared to P. So when you contract, will you expect the distance to be more or less? Now, we'll always expect the distance to be less. So is this correct? No, absolutely not. So we know the answer will be T. Okay? Okay, next one. Which of the following does not, again, does not produce an effective convection current? Okay, so the key word here is effective. Okay, is it able to produce convection current? We'll run through all the options, but the ideal answer is always one that's effective. So when you have this kind of question, usually they're asking you for the best answer. Okay, best possible answer. So there's going to be ideally 2 or 3 answers that will be correct and will be accepted. Okay, so you got to run through and you got to see whether is it, does it fit for you. Okay, so let's look at it up. Okay, so we know air conditioners. Now, air conditioner, the purpose is to keep a room cold, right? So which is why they are placed at a higher position. Now, why? We learn concept. So we go into the concept. We know that hot air rises and we know cold air sinks. Okay, so hot air rises, it converts the hot air into cooler air and then it sinks. So we know this is effective. Yeah, it's quite effective. Okay, not too bad. Cooling fans. Cooling fans are installed behind the refrigerators. Okay, so cooling fans are there to cool the refrigerator back. Okay, the back. Now, if you've touched the back of the refrigerator, it's actually warm. So cooling fans, in this case, they say they are installed behind the refrigerators. Now, do you want to cool the back of the refrigerator? Are you sure? Not sure about it? Okay, never mind. We move on to the next. Okay, we see. Is C and D is considered as effective. Heating coils in an electric kettle. Okay, so electric kettles, the purpose of the electric kettle is to make something warm and keep it warm, right? So when heating coil is placed at the bottom, that means the bottom of the liquid will heat up and then it will rise. Effective. Okay, so far we found 2 effective. Okay, so this word take first. And the next one, heaters are placed on ground level. So what do heaters do? Heaters work opposite of an air conditioner. Okay, so heater job is to turn something into cold, into warm. So where do you find this cooler air? It's always found at the ground level, right? Cold air sinks. So it's always on the ground level. Heaters will take this cooler air, convert it into warmer air, and then the warmer air will rise. Is this effective? Yes. Then you realize, oh, okay, so cooling fans are not very effective. Cooling fans at the back of the refrigerator have an effect, but is it the most effective way of removing the warmer air at the end? No. Why is there warmer air at the end? Refrigerator's purpose is to keep something cold. So the hot air in the refrigerator has to exit, right? So they'll exit by what we call the black fins, which is found at the back of the refrigerator. So cooling fans in this case are installed to ensure that the back is not warm and it keeps the air ventilated. But it's not the best and effective way. So in this case, the question is asking you does not produce the most effective. So we'll take as B. So it's a bit of a tricky question, but yet can solve. So if you cannot get the answer, you're not sure, always go to the next options and see whether you can get an answer derived from it. Okay, question 4. Question 4 is a pretty relatively easy question, but let's look at it. Okay, here you have different surfaces. Now, what do we know? Surface can reflect, they can absorb, and they can always emit your radiation. Okay, that's what we know about our surfaces. So all these surfaces, how does it help? How does it work? So they either can absorb heat or they either can release heat, right? Based on the type of surface. So what do we understand? We know that black and dull surfaces, they are good absorbers of heat, good emitters of heat, right? And then you have the silver, white surfaces. We know they are your poor emitters, poor absorbers, but they are good reflectors of heat. Okay, that's what we understand. So we need to find out here which of the following comparison is correct. So if you realize you look through, just run through all the 4 MCQs, you will see that the MCQs here, they're interested in emitting radiation, reflecting, and absorbing. So you need to see very clearly and carefully. You cannot just straight away jump onto one. You have to go option by option. Okay, so let's look at it. Okay, so here you are given the key here. So we use the key to help us understand, okay, what it actually is. So silver. Now, I always do this way. We always look at the front, the back. Okay, then you can see the trend. Okay, so let's look at silver here. Now, silver. Does it have the best radiation? No. Does it have the worst absorbing radiation? Yeah, likely. But do we know that this is the answer? No, we know definitely it's not correct. Okay, just by the first one, we know already it's not. Okay, the question one, which one is correct? Now, next one, B. Silver. Worst reflecting? No, it's actually one of the best, right? So we know, okay, wrong. Cross out. So they see you're left with 2. Okay. C. Silver. Emitting radiation, not the best, right? But dull black is the best. Okay, not the best, worse. Okay, let's look at it. Reflecting, yes, it's the best. Okay, so we know, yeah, this is likely going to be the answer. We just check D just to confirm, okay? Silver, worse in emitting radiation, in reflecting. Okay, we know it's wrong, copper wrong. Because reflecting, it is actually one of the best. Okay, so we know directly, we get the answer C. So if you have any questions as I'm moving along, please don't hesitate. Let me know, okay? Just type it in and I will be able to receive the questions and I will answer, okay? As we move along. Okay, next one. Thermoflask. Now, which part of a thermoflask reduces heat transfer via radiation? Okay, how about we have a little interaction? How about for a change, you give me the answer. What do you think the answer would be for number 5? Which part of a thermoflask reduces heat transfer by radiation? Okay, I'm sure you are able to reply. So how about you just type it very quickly? What would your answer be? How does it reduce heat via radiation? Okay, so thermoflask, how does it reduce heat via radiation? Now, thermoflask has various components. You have the plastic cap, you have the shiny inner lining warning, the walls, okay, silvery walls. It actually helps to reduce heat loss by your conduction and your convection, right? Now, in this case here, we want to know how is it reducing via radiation. Okay, so our focus here is radiation. Okay, radiation we know occurs because of infrared waves, okay, that are emitted. So plastic cap, is it by radiation? No, plastic cap we know is by conduction, right? This is a non-conductor of heat, right? It's a non-metal. Then you have the matte plastic surface. Again, you have plastic and it's matte color. Is it going to help with radiation? Right? Also, we know it's by your conduction. Okay. Now, shiny wall. Yes. This is definitely going to be radiation, right? Reduces heat transfer. Now, what about vacuum? Vacuum, is it able to reduce heat by radiation? No, it reduces heat by conduction and convection. Okay, why? Because vacuum means there is no particles present, right? So when there's no particles present, then conduction and convection doesn't take place very easily, right? You need a medium to be present. Okay, so you need medium to be present for your conduction and convection. Okay, so great. We've got our answer here, which is C. Okay, moving on. Here you have a plastic bottle that's filled to the brim with cap and is placed in the freezer. Okay, so that means a plastic bottle, you put inside the water, you put in the freezer. I'm sure some of us have done this before, right? We put inside, then you realize when you take out the next day, what actually happens to the bottle. Now, what actually happens to the bottle is we will realize, okay, we've done this before, the bottle actually cracked. Now, this is a little confusing. Okay, now why did the bottle crack? You were like, oh, it became ice, right? It's supposed to contract. Actually, no. What happens is when ice form, actually what happens is the water, the molecules inside, they actually have expanded. Now, why does this happen? Now, water expands when it freezes. Now, water expands when it freezes because of the bonding in water molecules, which you will learn in the upper levels called hydrogen bonds. Okay, so they don't have a very good and tight fit. So as a result, what happens is they expand instead of contracting as a result. Now, this kind of questions, when they talk about water expanding when it freezes, is a very common question. So it's a concept that you need to know, okay? Now, this is also one of the reasons why ice floats on water. Okay, so it actually explains why ice floats on water. Okay, due to this, because water expands when it freezes. Okay, so when it expands, that means we are saying heat, right? It actually rises. So as a result, ice floats. So these kind of questions are pretty normal. Okay, so let me just write down the concept here. So water freezes when it expands. Okay, and we will say water contracts when it melts. Okay, so actually quite the reverse happens. This is important concept they like to ask, okay? So just take note of it. Okay, great. We have number 7, moving on. So you have a cameraman, he's cooking a cooking marshmallows using a metal fork. I'm sure some of us have done this before, right? Over a session. Now he holds it over the fire. So which illustration below shows accurately how heat is conducted from the metal fork to the camper head? Okay, so it represents accurately, we're talking about heat conduction from the metal fork to the camper's head. Okay, so we're just talking about heat transfer here. So all the question is asking you, how does this heat transfer take place? So the question here gives you an illustration of heat transfer, but in terms of diagram, okay? They didn't use words. So before hitting the metal fork, and then they give you after hitting the metal fork. So what happened when metal is heated? Now, when your metal is heated, we know that the atoms will vibrate, right? It's solid, right? They're closely packed. So atoms vibrate, and then they will collide with the neighboring atoms. So when they collide with the neighboring atoms, they will transfer the heat energy. So when they collide with the neighboring atoms and then they transfer the heat energy, that's how heat transfer in a metal. Of course, metal, besides having the atoms, they also have what we call electrons to transfer energy, okay? Which is why metals, they are better conductors of heat. Compared to your non-metals. Okay, because of the presence of the electrons, so they can transfer heat at a good rate. Okay, so now we are looking for an illustration in terms of diagram that will explain this process throughout. Okay, so we're going to look at it very carefully. So let's see. Okay, so here we have the metal fork that is being heated. So when it's being heated, we know that, okay, we don't expect it, before it's heated, my bad. Before it's heated, we don't expect it to be vibrating. So you can see the first 2 diagrams, it actually looks like it's being vibrating, right? They're moving. So we know from here, okay, let's eliminate A and B immediately, okay? So we know before heating, okay, great. Then as it's heating, you are transferring heat. So now you compare between these 2 diagrams, between here and here. Okay, so when you start to heat, you always heat from the left to the right. It doesn't just start from the middle. Okay, so heating is always from one end to the other end. Okay, so you start from here, then it collides. So as it's colliding, all the atoms will still be vibrating. So it's not correct for this diagram to say it's not vibrating. It's also incorrect to say that this is not vibrating. Okay, so they all will be vibrating, collide, collide, all the way until the heat is transferred from one end to the other end. Okay, remember we learned in conduction, heat is transferred without movement of medium. Okay, so medium refers to a solid or liquid or gas. Okay, so if you're not sure, medium is referred to a solid, liquid, or gas. So if you see this word medium, then you know immediately, okay, we are talking about solid, liquid, and gases. Okay, so very clear. Here, we know, we've got an answer. Very nice. C. Okay, next one. About expansion and contraction of water. Okay, so we went through just now the concept, right? Expansion and contraction of water. We want to know which one is correct. Okay, so let's look at it again. So what do we understand just now? What was our concept? Our concept say very clearly that water freezes the volume expands, right? That's what we know. Then we also know that when water melts, okay, the volume contracts. So the reverse happens. Okay, this is our concept. Okay, so we have this in mind. We're gonna look at it. Okay, one by one, which of the following statements is correct? Okay, when water is heated from 0 to 4 degrees, its volume expands. Okay, so what do we know first thing first? Melting point of ice is 0 degrees Celsius. Okay, something that will help us, okay, in answering the question. Now, when water is heated from 0 to 4, its volume expands. Okay, when water is heated at 0 degrees Celsius, it's actually a ice. So as you are going from 0 to 4, you're actually melting. So when it's melting, does it expand? No. We know it contracts. Okay, that's what we understand. So we know very clearly, okay, yes, the answer is my B. But let's look at it. Next one, let's look at C and D, okay? So when water is cooled from 4 degrees Celsius to 0 degrees Celsius, its volume contracts. Okay, so 4 degrees to 0 degrees Celsius, here it is freezing. Okay, it's going through freezing. Now, if it's freezing, does the volume contract? No. We already know that it expands instead. Okay? Can? Something to take note. So we know from 0 to 4 here. Let me just put a note here. It is melting. Okay, like I said, if you have any questions, please let me know. Okay, you can type it into your, and I'm sure you can see the little box of questions. Okay, you can just type in your questions and I will answer them, okay, as we move along. Okay, here, great. We have an answer. So like I say again, this concept is important. This question came out twice here. So again, in this question also, we spoke about the same thing, right? Water cracked, water expanded. So when it freezes, the water expands. So like I said, the concept has got to do with the bonding in water. Because water is actually H2O, as we already know, right? So what happens is water molecule actually looks like this. Okay, in terms of the bonds, it looks like this. Okay, so we call these hydrogen bonds. So it has got to do a little bit about its lattice structure with the bonds that it has with oxygen that actually contributes to why it actually expands when it freezes. So again, this is something, a concept that you will learn in the upper levels. So for your syllabus, don't worry, they will be asking you this, but you need to understand, okay, this simple concept. Water freeze, volume expands. Water melts, volume contracts. Okay, simple as that. This is a simple concept. This is the only thing that you need to be able to understand. They will not ask you why. Okay, that one is way ahead of your level of study. Okay, so we have been working on our 8 MCQ questions. Okay, so these MCQ questions, like I said, very much exam based. Okay, they tend to ask this kind of question, especially this question 2 about your expansion and contraction of your bimetallic strip. So always remember when the bimetallic strip expands, okay, of course we know that it should expand the most. That means we know like a larger, in this case, greater distance. Then when it contracts, the reverse will happen. Okay, it will no longer be a smile, it will be like a frown. All right. So this one is also again another important concept by metallic strip. You also must know how to explain conduction, convection, and radiation. Okay, which we'll cover in a bit. So let me just do it here. Okay, so we have 3 types of heat transfer. You have your conduction, convection, and your radiation. Okay. Now, when we talk about conduction, we know it's mainly solids, correct? Because there is no movement of the medium involved. So they just basically transfer energy. Actually, not basically, all of them transfer energy. Okay. So always remember, they do not transfer the molecules. The atoms don't move, the molecules don't move. When they collide, due to their movement, whether they are vibrating about their fixed position, or whether they are sliding over one another for liquids and for gases where they move at high speeds, through the collisions that they have with other atoms and molecules, then they transfer the heat energy from one place to another. Okay, so one point to another. Okay, in convection, it's mainly in fluids. Okay, fluids are usually referred to your liquids and gases. Now, why do we use this? Because there's movement of medium. Okay, for convection current to take place, there must be some movement of medium. Okay, another important thing is your convection current. Okay, super important. You must be able to explain convection current process. Okay, so let's look at just quickly go through. Okay, so convection current, how does it happen? Very simple. We know that the hotter fluid, okay, it can be liquid or gas. See, fluid gets heated up. So when the fluid gets heated up, it expands. Okay, so, and then it rises. Okay, so this is what happens. So then what happens is the cooler fluid, it can be again, like I said, liquid or gas, again, because it must be able to move freely. Your cooler fluid is denser. Okay, so it sinks. So one rise, one sink. One rise, one sink. Okay, so rise, sink. So usually it's like a circular, right? So what happens is again, convection current is set up. So your convection current, important this one, due to a difference in density. Okay, because rises, that means we know it's lower density. Then when it sinks, we know that it is denser, right? So because of this imbalance in density, one rise, one sink, then you have a convection current setup. Okay, so this is a very important concept. Now, can solids go through convection current? Now, what do you think? Solids, can they go through a convection current? Not really, right? But can convection take place? Can. Okay, so we always say solids for them is the least. We don't use the word cannot. In secondary level, it's always a word's called most and the least. Okay, so it can actually take place, but very slow. Okay, it's very insignificant. Mostly, you will be able to see the movement in your liquids and your gases more than in your solids. Okay, so let's look at radiation here. Okay, so what about your radiation? Now, radiation, of course, happens due to your infrared rays. Okay, these are actually heat source rays. Okay, they come from the sun, or it can be from any heat source. Okay, not from only the sun, the heat source. So they emit these rays, and as a result, radiation can take place. Okay, so you can be sitting around a fire, right, like a bonfire, and then you have heat reached to you by your radiation process. Or you just stand in the sun, there's sunbathing, sun tanning happening, and you're also getting your heat via radiation from the heat source. Okay, so the thing about radiation is they're very interested in the type of surface. Okay, type of surface that you went through just now is extremely important, and it helps you understand why it is absorbed or reflected. Okay, so let's look at it. We have the question. Here we go. Okay, so what do we know? Okay, so we know that if it's a black, dull surface, we know that it is a good absorber, good emitter. Okay, emitter, another word for it is radiator. Okay, you can use emitter, you can use radiator. of heat. Now, but it is a poor reflector of heat. It cannot reflect heat away, okay? So no matter what, it's going to be absorbed. So if you're going to wear like a very dark base top in a very hot, heated environment where there's a lot of light rays and heat rays, you are going to feel warmer than usual, okay? So you wear lighter colors and you'll feel a bit more cooler. Okay, so when you have, we can say white, shiny, smooth, okay, all these white and shiny surface. We talk about smooth and rough later. Okay, so white shiny surface, they are poor absorber. They don't absorb very well. Okay, they're also poor emitters. Now, when I say poor absorber, poor emitter, it means slower rate. It doesn't mean cannot. Okay, good means better. That means it is better than the other. When I say non-absorber means completely cannot. So be very careful with the words, okay? So it's a poor emitter of heat, but it is actually a very good reflector of heat, okay, compared to your dull and black surfaces. Okay, so this concept is actually quite important. Okay, so having all this concept in mind, let's look at our section B questions. Okay, so we have two questions here that we are going to do. So let's look at it. Okay, here we have two conical flasks, okay, with different exterior paint. So what are we interested in is the type of paint. Okay, it's different. You have equal volume of air. So you are told the initial temperature of the air is the same. Okay, so you see I'm highlighting as I'm reading. So I'm only highlighting important points about the question. So different exterior paint. So that's what that's changing, which we call the independent variable. Okay, equal volume of air, initial the same, and they are both placed under the same sun. Okay, so we know all these are the constant variables. Temperature initially constant, volume of air is constant, and then you're placed under the same sun, that means the amount of heat energy is also constant. So definitely, as you can see here you have one with aluminium paint, and the other one is with the black paint, okay? So aluminium is a metal, good conductor. Black surface, like you went through just now, is a good absorber of heat, and inside you have air. Okay, name the process by which the energy reaches the sun. So like we went through just now, it's your radiation. Okay, heat from the sun is through radiation process. Okay, describe and compare the temperature of air in both flasks after some time and explain your answer. Okay, so let's look at the question. What the question demands. Okay, that means your answering skills first, before we dive into the answer completely. Okay, so here they're asking you to do two things. Describe, then compare. Okay, and then explain. So there's actually two things. Then you're going to explain what you are describing and comparing. Now, when you describe, you're going to use information from the question. Okay, when you are comparing, you are looking at the two experimental setups given to you. So all this is from the question itself. Okay, all this information. So just by looking at this, we know that the temperature increase, right? We want to know the temperature of air, right? Temperature increase in the conical flask painted with the black paint would be greater than the aluminum paint. Then you're saying, hey, but aluminum is a conductor. Yes, it is a conductor, correct. But it is also shiny because it's a metal, right? It is a metal and metals are actually shiny, right? They have a shiny surface. So this makes it a poorer absorber of heat, right? It is a good reflector. So that means whatever heat that goes or touches the conical flask, the tendency for it to reflect is way much higher than it will be absorbed. Okay, so this is what we know, right? We can use the information and then we know the comparison. In the black paint, it will be greater. Okay, so we write that first. So when I say describe, I just take information from the question and I'm doing a comparison between the two of them. Okay, when you compare, you must tell me about the black paint in comparison to the aluminum. You can also write about the aluminum paint in comparison to the black paint. because the question here didn't specify which conical flask they are focusing on. So you can talk about the black paint, I can repeat, in comparison to the aluminium paint, or you can talk about the aluminium paint in comparison to the black paint. Okay, that's pretty much fine. You can choose either way. Okay, so I know that the increase in temperature of air in the flask painted. So we know black paint, so painted with your black paint is greater. Okay, so the temperature will be way much greater. Then the temperature, okay, so we have to do a comparison, right? So you have to link it back to the temperature of air in the aluminium paint. So you cannot just stop here and say full stop is greater, full stop, cannot. Because the question say compare, okay? So I must link it back to the other. How does it differ, okay? Greater than who? Greater than the temperature of air. So why I say temperature, I cannot just say conical flask, because the focus here is temperature of air, not temperature of conical flask. Okay, so we say painted with aluminium paint. Great. Okay, so this is what we have. So, okay, we already described. We already compared. Now what we need to do, we need to explain. Okay, so why? How come it's greater? Now, what do you understand from your theory? Black paint is black is a good absorber of heat. So we'll say, okay, black surfaces are good absorber of heat energy. Okay, compared to shiny surfaces. Okay, so again, I must do this because I just say compare. Now, you must be able to derive that aluminium, despite being a conductor, it actually has a shiny surface, okay? Which is why it's a poorer absorber and it's a better reflector of heat. So then, we know that because of this, so we know that the conical flask, okay, with the black paint, gains heat faster by radiation. Okay, so I say clearly, by radiation, because you are gaining heat from the sun, right? Then of course, by your conduction, it will transfer to air. So here we are focusing, so you see I use conical flask. Conical flask is the one that's gaining heat here. So I'm going to be doing this. Can? Okay, so by radiation. So because of this, we know that the air inside, I'm doing it right. It's repeating what we are doing just now. Okay, so here we have the answer. Describe, compare. First portion. Here we have the description and the comparison. Okay, let me just write here. Number 1, number 2. So I have the 1 plus the 2 here. Then we have the third portion here, which is the explanation. Okay, so you put them together, you will get your 2 marks. Okay, as your answer for your question. Any questions so far? Anyone has any questions? Okay, please put in your questions and then I'll answer them, okay, as we move along. Okay, here, number 10. Now, an experiment here to show that water is a poor conductor. Okay, so they already tell you that an experiment is conducted. What are we trying to show? That water is a poor conductor of heat. So this experiment is conducted to prove, yes, indeed, water is a poor conductor. So water is a poor conductor will be your hypothesis here. Okay, so let's look at the diagram first. So I have water, I have a metal rod. Okay, great. Metal is a very good conductor. I have a wire gauze, I have ice. So I roughly know, okay, maybe they're trying to melt ice, right? And I have a Bunsen burner here, so that means I'm heating this part of the water. Okay, so I know that my warmer liquid is going to be here. So this portion here, my liquid is, my water is warmer. So what do we know about warmer water? It rises and it's already at the top. Okay, so now let's look at it and then we see whether the ice eventually is able to melt. Okay, something food for thought for now. Okay, function of the wire gauze. Why do we have this wire gauze here? Okay, you realize that you have water, you have ice. What are we trying to reduce or trying to prevent? Is there to, of course, act as something, prevent something, or not to allow to do something? Now, ice. What do you understand about ice? Ice floats. But here, the ice sinks. Okay? So when you have a gauze, it's actually like a little layer of covering. I'm sure you have seen a wire gauze. So it doesn't allow the ice to go through because the little holes are actually quite small. So the ice cannot go through. Okay, so this is to prevent the ice cube that you have at the base, right? Prevent the ice from floating as it is. So this is something unusual, but then the wire gauze actually helps, okay? It prevents it from floating, so it keeps the ice at the bottom. So then we know, okay, because if it reaches to the top, it's going to melt immediately, very fast, okay? And then defeats the purpose. You cannot tell the experiment. So what is actually going to happen is eventually over time, we want to see whether will heat be able to be transferred to the bottom, okay? Water, whether is it able to transfer heat to the bottom and see whether the ice actually melts, okay? So we'll analyze it in a bit. So water is heated. What happens to the density? Explain your answer. Okay, so water is heated. We want to know what happens to the density. Okay, and then they say explain your answer. So state what happens and then explain. Now they ask you to use the density formula. What does the density formula tells you? Okay, so we read the formula up first. Density is mass over volume. Okay, this is what we know. So let's look at it. When water is heated, it expands, right? When it expands, that means the volume increase, the density will decrease. Okay, so we know, okay, very quickly, density decreases. Why? Okay, so when water is heated, it will expand, okay? So volume of water expands. Now take note, when expansion takes place, okay, it is not that the molecule or the atom becomes bigger. When I say volume expands, okay, something important. Volume expands, that means there's an increase in the empty spaces, okay, between, we will say, the molecules or the atoms. So the empty spaces increases a little. So every empty space increase all the thing, increase a bit. So eventually it leads to a large increase, okay? Because every single thing is increasing. Okay, so water expands. Sorry, what am I talking? Sorry, volume of water increases and water expands. Okay, so this is what we know. So how do we apply the density? Okay, so volume increases. This thing goes down, okay? They have an inverse relationship. Whenever volume increases, density will decrease, okay? It's an inverse relationship. So what happens here? How do we use the concept of density? Now, volume and density is affected, but what happens to the mass? When you are heating something, does the mass change? No, the mass does not change. Okay, very important. We call it physical change. Mass remains the same. If you are heating, that means water is becoming steep, right? I'll come to this concept in a bit. So water becomes steep. But is it the same amount of water converted to steam? Yes, because mass is conserved. So that means mass is kept constant. All right, so since mass is kept constant, okay, with an increase in volume. Okay, density increases as, so you can write about the density formula. Okay, density is mass per unit. Okay, so steam, another concept. Now, very important, when water boils, you get steam. Okay, not water vapor, steam. When water evaporates, you get water vapor. Okay, concept that some students always confuse, but something good to know. Okay, water boils, you get steam. Water evaporates, you get water vapor. Okay. Okay, moving on. Convection. Now, how do we define convection? Okay, so what is your convection? Now, convection we know happens because of the movement of fluid due to convection current, right? So how do we define it? So we know that it is okay, it is the heat, sorry, it's the transfer. We transfer heat energy, transfer of your heat energy from one point to always transfer from one point to another. Okay, you can say one place to another, but one point is better. Okay, one point to another by the movement of the fluids. Okay, we say fluids because, like I said, fluids refers to your liquids and your gases. Okay, so by the movement of the fluids, due to a, of course, we know difference of density. Okay, there's also another way to write it. You can say there's a transfer energy from one point to another by the movement of fluids, setting up convection current. Okay, so the difference in density, in this case, they will set up your convection current. Okay, can? Like this is how I explain to you, right? Hot rice, cold sink. Okay, come, next one. Why the water in the setup above is unable to heat up evenly? Okay, so here, they're asking you how come it cannot set up, cannot heat up evenly. So that means they're telling you, okay, no convection current. If you cannot heat up evenly, that means no convection current. So here is warmer. Can the warmer liquid sink? No. We know warmer rises. So that means the warmer liquid remains at the top, the cooler remains at the bottom. Is there any convection current being set up between the two of them? No, it does not, because you're not heating the base, right? So the cooler remains cool, and then the water that's heated up remains warm. Okay, so what happens as a result? Can you have a convection current set up? In this case, no convection current will take place. So they're asking you why not. Okay, that's what they're asking you. Why not? They are telling you it does not take place. Just why not? Okay, so water at the top, say it's heated. Okay, its volume increases and it rises. Okay, so the warmer, so we know that the warmer water, it remains at the top. It does not sink, okay? And the cooler, we say the cooler water remains at the bottom. Okay, so as a result, convection, or you can say no convection. So very easy, no convection current is set up. Okay, and heat is water is not up evenly. So you have two aspects, the warmer and the cooler liquid. Okay, define conduction, definition of conduction. So This one is quite simple, right? It's just simply the transfer of your heat energy again from one point to another. We'll say without the movement of medium, okay? So like we say in the solid surfaces especially, what happens is they actually vibrate about their fixed positions, right? There is very little movement of the medium. They only vibrate about their fixed positions, and as a result, they transfer from one point to another. All right, just keep the questions coming, yeah? Yes. Okay, so conduction is actually better takes place in a solid surface, a solid object. In liquids and gases, it's actually better for them in terms of convection. Yeah. So when we talk about conduction, there must be some surface. So you have one surface has to be a solid. The second medium can be a solid, liquid, or gas. So let's say I have a solid surface, and then my second medium is actually a gas or a liquid. It touches my surface, which is solid. It is still conduction. Then within the fluid, that means within the liquid and within the gas itself, then it will be convection. Okay, which is why heat transfer when it happens, it only doesn't happen by one. It can happen by two or all three: conduction, convection, radiation, all together. Okay, so with reference to conduction and the setup above, okay, so that means here we are talking about conduction and the setup. Okay, that means the experiment that they give you here, and from what you understand, okay, like we went through just now, the definition of conduction. Why ice does not melt? Okay, we understand already, right? The heat transfer didn't take place. Convection current didn't set up, right? So they say that even when the water at the test tube at the top is boiling, okay? So simple. Why it doesn't happen? So we know convection current didn't set up. We agree. But then again, heat can still transfer, right? Because it's a liquid, fluid. Heat can transfer from one point to another. So what are we using? Water. Now, water is a poor conductor of heat, just like how air is. Okay? Air is also a poor conductor of heat. So that means heat energy from the top of the test tube. It's not that it will not conduct, will be conducted very slowly, okay, to the bottom. Or we'll say to the ice at the bottom of the test tube. Okay, so hence ice in this case does not melt. All right. Okay. So I hope this session was good. You're able to understand better about revise about your transfer of energy and also about the effects of heat in the expansion and contraction. Okay.